then we move on with the third end in this session, the last presenter, Mohammed. Yeah, you've probably seen all to switch all these things up. Great. Yeah. Chris.
Hello everyone, my name is Muhammad Ameen al-Siaghi. I have a long name, just as my title. So I'll be talking about the conversion of anaerobically digested sludge for resource and energy recovery. So why did we do sewage sludge? It's because it's a big problem, it's a pollution, it's a health risk, and also it's because it generates a lot of sludge. Specifically in Netherlands, it's estimated generation is 353,000 kilogram per year. And why we chose sewage sludge is, as I told you, the sewage sludge is currently treatment is not efficient, is done by drying, as we mentioned before with our colleagues, and then it goes to incineration. So the problem with this is energy intensive, and also incineration requires gas cleaning, and also there is no resource recovery, and also requires the transportation of the sludge from the wastewater treatment plant to the incineration plant. So the solution is the hydrothermal carbonization, which is done to recover and treat the sewage sludge at the site of the wastewater treatment plant, and it also improves the dewatering process, and also recovers, as I mentioned, the resources such as energy and nutrients. So what is hydrothermal carbonization? Basically, it's a pressure cooker that operates in autogenous pressure. So it starts from atmospheric pressure, and then it goes up to 16 to 30 bars. And also it operates from 180 Celsius to 250 Celsius. And the reaction times can range from 13 minutes to 24 hours. So again, to the worldwide application. So this can be applied to anything, not just for sewage sludge. It can also for fecal sludge, because as long as humans require sanitation, they require to handle their wastes. So this is the beautiful thing about hydrothermal carbonization is the hydrochar. So the hydrochar, as you can see, as this one. So there's many applications for the hydrochar. One of them, as my colleagues say, the soil amendment and for solid fuel, and also for air and water treatment, and also for biogas enhancement in the anaerobic digester, and also for carbon-based products such as batteries for negative anode, and also HTC liquid can also be used to recover biogas, to generate biogas, and also for as liquid fertilizer and bio-based chemicals. So the research gap is, the problem is with hydrothermal carbonization is widely researched, especially in sewage sludge, and because it's more applicable in sewage sludge rather than other biomasses. So the problem with sewage sludge is different from one place to another, as reviewed in a paper. You can see the composition of the elemental analysis is different, and therefore gives you different applications and different characteristics. And also you can see that not only the place, also the collection point in the same wastewater treatment plant will affect your hydrochar and the HTC liquid, and also will lead to different outcomes. And also the most important thing is the full inorganic analysis and distribution. So this research haven't not been measured by any of the journals for wastewater treatment. So the research objective is to characterize the raw sewage sludge at different points of the collection point of the wastewater treatment plant, and also to do the mass balance and elemental balance, and also to characterize the hydrochar and liquid obtained from the HTC process. And then later on we use those characterizations and elemental analysis to see the potential valorization. And we would hope to, we answered those questions in my research to see the properties of those raw materials and the mass balances and also the elemental balances, and also to see the effect on the HTC products, and then we localize what is the best place to put our HTC in the wastewater treatment plant. So basically I did my research with Delftland Water Authority, and I took my sewage sludge from Harnesfolder, and this is just the sewage sludge treatment process. The wastewater treatment process is a bit complex, so it goes to the anaerobic digester from the primary and secondary inflow. So the settling tanks, so you get some solids, and then the liquid goes to the water treatment. So we get here is the solid, and then from the solids we get some biogas that was distributed to the network, and then we have a buffer tank there that we add magnesium hydroxide, and then we goes to the dewatering process, we add polymers, and then after the dewatering we transport it to the drying and then incineration. So there's the same solid content for both point that we did, so point A and point B. So, but after storage, the characterization actually changes. So the methodology that I use is the HTC process, and then the mass balances that I did from the product, and then the elemental analysis, and also to do the valorization potential of those of sludges. So this is the schematics for the HTC that we used in the liquid in the laboratory. So this is take 1,300 grams of sewage sludge, and then we process it in 180 for 2 hours, and also then we do the measurement through the balance through the gas measurement, and then the liquid after receiving and filtration, and also we do the HTC analysis, the elemental analysis through different various procedures and standards that we use in the lab. And then we did the calorific calculation value for the hydrochar and for the raw sludge, and then also from the of the total carbon, we could get the potential valorization. So everything that we did here was done in triplicates. So you can see that in the results and discussion that we have sample A and sample B. So sample A was run in the HTC 3 times, and sample B was run in the HTC 3 times. So we get the gas percentage, which almost 2%, and then we have the liquid percentage that was approximately 40% to 45%, and then we have the solid yield percentage, which is, it goes from 55 to 64%. So the main message here is the gas production is very low. That means we don't have that much impact on the environment, and also we have a high amount of liquid and solid that we can later use for the recovery and energy recovery and resource recovery. So then again, the elemental analysis, I started with the organic elements. So I'm doing the carbon and then nitrogen. So you can see that this is the raw sludge, and this is after the HTC, and you can see that this is the color of the solids, and this is the liquid, and this is the gas. So this is the raw, and this is after the HTC. So you can see that this is mainly in the solids, and then what happened is the solid shifts to those different kind of products, the gas, liquid, and the solid. So this is for carbon, but for nitrogen, it mostly stays in the liquid, it shifts and leaches to the liquid. But for carbon, you'll have carbon emissions, so CO2 emissions, but it's not that significant. So as well, so what we can get from this graph is that we can use this, valorize the carbon potential in the HTC product, and also we can valorize the the nitrogen in the liquid product as maybe fertilizers. So again, the inorganic balance is we did a total of 16 inorganic elements, but what we show here is the most significant. It goes again the same colors for the solid and the same color for the liquid, and then it's also estimated that there's no gases there's no inorganic that goes to the gas phase. So what happened here is that you see that this is the sample A, and this is after the HTC, and this is for phosphorus, silica, and calcium, magnesium, and iron, potassium, and sodium. So as you can see here, that sodium and potassium can leach out to the liquid, so it actually improves the hydrochar. And also for phosphorus, it leaches out to the liquid, but it does not leach out for sample B. It's because of the formation of strobite. By adding the magnesium, it actually forms strobite, which is the term of phosphorus with nitrogen and magnesium. So the potential for valorization is through energy recovery and nutrient recovery through strobite. So firstly is the solid fuel potential for valorization. So for sample A, it is calculated that the hydrochar has improved in the heating value by 15% from the raw sludge, and for the liquid fuel, it is the calculation estimated to produce 0.0074 cubic meter of methane per liquid of HTC liquid. And this is based on a journal and study that was done. Is by using this process for the same characteristics, we can actually recover 80% in strobite by using acid leaching, and then crystallization, and then we have strobite, and then clean hydrochar. So also the added value product. So the highest thing is the added value product, because it is what you can invest in. So as you know now, the world is transiting to electrical cars. So we can use that hydrochar in the lithium-ion batteries, and also because of the hydrochar having high amount of iron and aluminium, so we can have a magnetized hydrochar that we can actually put it in as an anaerobic digestion medium, and also we can use it as mycolis in the wastewater treatment for heavy metal removal, and also as anaerobic digestion additive. So this one actually at the same source, at the same wastewater treatment plant, so that's why we don't have to have the transportation cost. So back again to the number that I told you about. So from that number is we can estimate that in Netherlands only that we can produce 1,100 cubic meter of methane per year, and also that would gives you a 45,000 megajoules of power per year, and also we can recover 5,000 of strobite per 5,000 kilogram of strobite per year. So the conclusion is, the first thing is we noticed that there's a difference in the characteristics of raw characteristics in the raw sample A and sample B in terms of CHNO content, and also the moisture content, and also for the ash content. Second thing is the mass balance and the organic analysis. So for the mass balance is slightly different, but they both have high iron and aluminium, but it tend to shift to for the phosphorus is different. That's my second point, is the inorganic distribution after the HTC, which is phosphorus and sample B tend to stay in the solids, and also arsenic is also tend to shift to the liquid, unlike the other heavy metals which tend to stay in the solid phase. So that's what that both sludges can have similar. And also the optimum HTC reactor placement is at point A, because as I told you, the qualification, the heat content is improved, and for the liquid potential to produce methane is the same for both of them, but for that reason, and also for the strobite to be able to precipitate strobite, is better to add the strobite, the magnesium hydroxide, after the HTC, not before the HTC. So my recommendation is to instead of using filtration and sieving, is to use a centrifuge, and then we go to dry, is because that's what they do in the industry, and that's more realistic. And also is to increase the solid percentage because my solid percentage was 3.4, which is very little. So we want to ideally increase it to 7 to 10% solids to minimize the energy consumption, and also to enhance the solid yield. And finally is to come in understanding with the harness bolter operators and Delftland to see what do they want and what they have plans for the future. And then after that is to have a setup for all those processes that we're going to implement in the wastewater treatment plant, which is, as I told you before, is a thickener, and then followed by the HTC, and then followed by the anaerobic digester, and then followed by strobite precipitation. That is all for me. Thank you very much. I will be happy to take any of your questions.
Thank you, Mohammed, with the long name and the long title. I
Yes.
hope it's okay if I just call you Mohammed for this session. We have some time for questions from the audience.
Maybe I can ask a
Yes,
question.
of course, please.
How did you choose a certain temperature and residence time for your experiments? Was it based on something?
Yes, it's actually based on literature review. So what I did is when I was choosing the temperature and the residence time, so that they have their own effects. But usually when you tend to increase the temperature, you consume more energy, and then you lose more carbon to the liquid. And also when you also increase your temperature, potassium and sodium goes back to the solid phase. So it's better it's cleaner. This is the optimum temperature and residence time for energy and resource recovery.
Let's go from front to back.
I have a question.
Yes.
During your analysis, did you find any traces of heavy metal in the sludge?
Yes, there is, but comparing to those results that I showed you, it's very minimal, but they tend to stay in the solid phase. But again, as you said in your research, and Karen's research is, even though it's a hydrochar, so it can actually absorb heavy metals if you use it for treatment for wastewater treatment. So you can recycle it back and then use it for absorption treatment.
What would be your recommendations for the use of the liquid phase of the HTC?
Yes, my recommendation is to use it for anaerobic digester to improve the mass yield, the methane production yield, because that's just in the wastewater treatment plant. You don't have to do any further treatment, and you don't have to transport it, and then you get energy, and then you can supply it to the grid.
You mentioned too many good stuff about like having the HTC in the sludge treatment in this plant. Do you expect like certain challenges in that process as well, like in scaling up?
Yes, actually, this is the thing that we need to. A lot of research is done, but they usually just stop there. They don't go to the full scale. But I think that's why it's recommended to do a lab scale first for the imagined process, and then from there we can go to the pilot scale and then to the liquid scale. And also to have, because also the sludge characteristic also change with time. So, because also with behaviors and activities in the region, the sludge characteristics change. So we would have like a range maybe, but that's for future research.
Let's move to the panel. Any
Yes.
volunteer? Yeah, Arvid?
I'm not a chemist, so could you quickly explain to me once more why you specifically need this magnesium hydroxide? Why do you need that specific
Yes, so
kind of thing?
so now they actually do it to have a stabilized sludge. It improves the dewaterability of the sludge, and also that from that also it can precipitate the strobite. But that's one of the issues is they want to recover nutrients, and they want to recover the energy, but the thing is, when you precipitate strobite now, they take it to the incineration plant, and then they have to pay a hefty fee to get rid of the sludge, and then the incineration plant will get the strobite, but in terms of ash, and that's a problem because you're separating solids from solids. So it's better to leach the phosphorus and then precipitate it, and then you separate liquid from solid, and then you would get your.
Okay,
Yeah.
thank you.
Thank you.
Just one small question.
Yes, go ahead.
So this is with reference to your nutrient recovery, and you are expecting people of different cultures, different regions to use it. Do you see any challenges in this, or
Yeah.
any
Yeah.
social aspects that will?
The thing is, when you see it in crystal form, when you just show them that's from the sludge, and then you show them in crystal form, and then also you show them the one that is mined, it's literally the same. So what's the difference? And then you can actually educate people, and if it's in the crystal form, but if it's in the sludge form, then maybe people would, okay, they was like, this is a problem, this is from sludge, and this one, they are more skeptical, but if it's in this crystal form, it's literally the same. So you can just, easier than using sludge as a fertilizer.
Yeah, then let me also ask you some question. One thing I was just wondering about, you made very clear that the composition of all the different sludges from the different treatment plants
Yes.
can be quite different, and even from one and the same plant it can
Yes.
be quite different. but I would assume that overall this treatment plant at Delftland in the Harnaspolder has a certain sort of pattern or certain unique characteristics that make it more or less representable compared to other treatment plants that you would find in other parts of the country or of the world. Are there some sort of unique characteristics of the treatment plant here that you consider quite sort of distinct for the Delftland setting, and how would that affect your findings?
Yes, so the thing is, as I told you before, this is the first research that does full inorganic element for the analysis for sewage sludge. So out there, there's no heavy metals like the characterization for the full inorganic spectrum. So this is the first, and then I hope that also other wastewater treatment plant, they do the same process to do the characterization. So now we would also have a comparison in terms of inorganic compositions. So what we have now is in terms of CHNO compositions, and it's quite different. But you can see it's within the range, but even a slight 1% can change your valorization potential.
Okay, so actually we don't fully know because the other treatment plants haven't.
Yes,
done
they
this
haven't.
kind of-
Yeah.
Okay. Thank you very much.
All right.
And I think we are good to close. Thank you. Yeah, I think with this last third presentation in this session, we also close this session. So thank you very much for your participation, and of course for your presentations for the three presenters. Then I would like to again invite you to go for coffee or tea or water or just a chat in the hallway, so that in the panel we can also do a quick assessment before we continue.